Hello everyone, welcome back. In a previous video, we introduced the four major components of machine learning. You have a predictor variable, which is the information you're using to attempt to make predictions. You have your target variable, which is the variable you're trying to predict. You have a model, which is your guess at the relationship between X and Y. And you have your loss function, and your loss function assesses how good your model is. How different is Y from f of X? So in this video, what we're going to do is we're going to focus in on something you're likely familiar with, which is linear regression. And the idea is that we're going to use this familiar context to work through these four steps in great detail to try to increase your understanding. So to get started, we're going to do our standard imports, NumPy and Matplotlib. And we're going to be working with a synthetic data set. So we're going to use some random seeding, np.random.seed 1, 2, 3, 4. So this way we get the same random numbers every time. And now we're going to go ahead and create our data. So we're going to say A equal to 1, B is equal to 1. Because we're going to be modeling the line Y equals X plus 1 with some random error. We're going to say number of points equals 100. We're going to say X is equal to np.random.rand 100. And then Y is equal to A times X plus B. And now we need to also throw in a random error. And we're going to assume that our random error is a normal random variable with standard deviation 0.2. You do rand n to get it to be a normal random variable. Oh, and these should say n points to be good coding stylistically. And that's our data. So now let's take a look. We're going to want to plot both the true function and the data points. So to do this, we go fig x is equal to plt.subplots. We're going to plot them on the same picture, so we only need one subplot. X.plot. To plot the true line, we use the fact that it can go through two different points, 0, 1, and 1, 2. We'll make it a black line. And we'll label this true model. For the data points, let's make a scatter plot. X.scatter, X and Y. Label equal to data. In order to see our labels, we need a legend. And now let's scroll down and take a look. Okay, we can see our data looks like the way that we designed it to look. It kind of sort of falls along the line, but there's also some random error. Now, this picture is nice because we can see both the real function and the data, but it's a little bit too nice. In the real world, we don't know what the line is. We just have the data. So the picture we would actually get is something that looks like this. And our goal would be, okay, we're given this data. We can see that there's some relationship between X and Y. Let's figure out what it is. Heck, it kind of looks like maybe we could fit this to a line. Maybe drawing the line through like right here along the main diagonal, if you can see my cursor. And so we're going to try to model it by an equation form Y is equal to AX plus B and try to find the best A's and B's. So to do this, we're going to create a function called linear model, which is going to take in X, A, and B. Something which is worth noting is in the equation y is equal to ax plus b, we're thinking of a and b as the coefficients, which we're going to try to learn from data, and x as being the actual input. But when you write the Python function, they're both going to be equal to, they're both just variables. All right, and this function is actually going to be quite simple because vectorized operations are great. So it's just return ax plus b. And let's see how well this does for various models of a and b. So we could say for I in range 10, we're going to let a be a random number. And we want a to be random between 0 and 2, since we know that it looks like our data is somewhat upward sloping. B will be the same. And let's just make a bunch of plots. Oh, and we also need to go look at our figure. Okay. So we can see some of these lines are somewhat close, other ones not so much. To my eye, it kind of looks like maybe the pink one is the best, but we really can't tell just by eyeballing it. And we need to come up with a systematic way of assessing how good a line is so we can pick the best one. And this is where the loss function becomes key. So in this function, we're going to take the loss function to be the mean squared error. We're going to subtract off each y value from each f of x value. Then we're going to square those, add them up, and divide by the number of numbers. You take the average of the squared error. So to code this, we define a function called linear mean squared error. It's going to take in 4 inputs, x, y, a, and b. We're going to define error to be equal to y minus the linear model of x, a, b. Error is the true value minus the prediction. And then we return error squared mean. So now let's rerun our plotting the lines, but plot them so that way the good lines look darker. So we're going to go ahead again and replot these 10 random lines. Let's create a new figure. Let's plot the actual data so we can tell how good it is. Okay, when we're doing our plotting, let's make them all the same color. And now here's a little bit of a tricky thing. We're going to try to make the good lines darker. So alpha will control how dark the line is, how transparent it is. And we could start off with 1 minus linear MSE. X, Y, A, B. And this seems like a good idea because if it was perfect, the error would be 0, and we would get maximum darkness, which occurs when alpha is equal to 1. But this could, in principle, be negative. So we also need to add in a max with 0. So that now we are going to make sure that our alpha value is positive. Subplots. PLT.subplots. Sometimes it's easiest to mess up on the simplest parts of the problem. Focusing on the complicated stuff like how to make the dark lines thicker, but anyways. All right, we can see this looks pretty good. This line here is super gray. we can't, and it's nowhere near the data. Whereas these lines down here, which are closer to the data, look a little bit darker. So now what we're going to do is we're going to try to estimate the best values of A and B by trying tons of different combinations and picking the one with the smallest error. So to do this, we're going to first plot the data points. Fig x equals plt.subplots with an s, x.scatter. So now we're going to say for I in range 100, we're going to do the same trick of A is equal to 2 times np.random.rand. B is going to be the same. Predictions, preds, is going to be linear model of XAB. Error is linear MSE, linear with a lowercase l. And let's go ahead and plot our line. X.plot X versus preds. Let's make the color equal to black. Transparency equal to 0.2. And line width equal to 0.1. There's going to be 100 lines here, so we want to make them kind of like not so thick. Alrighty. So now we're going to say if error is less than best error, then we're going to perform an update. Now you'll notice I didn't initialize the best error yet. So we're going to start off the best error to be infinity. Because now no matter what, on the first iteration, we're going to have our error be less than infinity, and that'll be our best error so far. All right. So say we found something that was better than the best. So then now best error is equal to error. Best A is equal to A, and best B is equal to B. So now at the end of this, we have best preds. Best preds is equal to linear model X, best A, best B. And we should also plot this one. So we type in x.plot X best preds. And to make this one stand out, we're going to make it red. So let's take a look. And, oh, we forgot to add in the data points. Oh, we typed in x.scatter and we didn't type in x.scatter with the x and the y. Alrighty. So now we got a ton of different lines. And we can see that our best line, which is the red one, goes basically through the data, and it does appear to be better than most of the other lines, if not all of them. It is better than all of them. Okay. And now let's take a look at what the best A and the best B are. Remember that the correct answer is 1. If we'd done a perfect job, we would get 1. And we see that we got 0.69 and 0.183. So that actually seems like a little bit off. I'm just going to run this again. I think there might have been a random fluctuation. All right, so we see it's not perfect, but they're both kind of in the neighborhood of 1. A is a little bit too small. B is a little bit too big. Say we wanted to make this better, one thing we could do is we could try using 1,000 points. And this will take a while because 1,000 is a big number. But now when we use 1,000 points, we see that we're starting to get pretty darn close. I would do it again with 10,000 points and we'd get even closer, but I don't want to make you sit there and listen to it. You can try it at home if you want. So to summarize, in this lecture, we did linear regression by hand. We generated some predictor data and target data, and we modeled the data using a family of one-dimensional linear models. We collected predictor data and target data. We defined a family of models and a loss function, and then we used this random updating to find the best model from the family. So there's a few things we did not get into. And the biggest and most important thing that I really want to warn you about quite starkly is that fitting the data is good, but it's not everything. And there is such a thing as fitting the data too well. You don't want to overfit. Because what we don't actually care about is fitting the data. What we care about is when we test this on new data, how well is it going to work? And so there is such a thing as overfitting, and we're going to talk about it a lot more later because it's a very common mistake, and it's something you really need to think a lot about. All right, so that's it for this video, but I'm also going to give you some extra bonus material for free. You can stop watching if you want, or you can stick around. It should only be another minute or two. No more typing. You get to sit back, relax, take a nice sip of your coffee, and learn some stuff we didn't actually get into in the main portion of the lecture. So first thing is that we just picked a bunch of A's and B's completely at random. And the thing about this process is it's stupid. We did it, but I did it. And I did it because it was the simplest thing to do, and I wanted to show you how the process works. But this is never what you would do if you were like doing this at your job and trying to do it the best as possible. So here's what you would do in practice from a conceptual perspective. You would start off with an initial guess of your A's and B's. We call them A0 and B0. And then based on how things work, you would come up with another guess, A1 and B1, which are better than A0 and B0. And then you repeat this process. You come up with A2 and B2, which are better than A1 and B1. Then A3 and B3, which are better than A2 and B2. And then you keep going until your model is sufficiently good. Don't stop till you get enough. All right. So if you've taken calculus, this might remind you, and to emphasize, calculus is not a prereq for this material. This is why this is in the bonus. So if you haven't taken calculus, don't worry. If you have taken calculus, however, you might note that this might remind you of Newton's method for solving equations. And indeed, the rule for taking a better guess, it relies on basically doing some calculus involving the loss function. And the name for this procedure is something called gradient descent. Gradients are like a derivative type operator, which you learn about in Calc 3. All right. So now I made you suffer through a minute or two of math. Here's what you do in practice. You type this exact line, these 4 lines of code. So scipy.optimize is a submodule of scipy, scientific Python, for optimization procedures. We want to minimize the loss function. We want to make it as small as possible, so we import minimize. And this is where things get a little tricky. It wants to learn those 2 parameters, A and B, as the 2 elements of a NumPy array. So we're going to minimize as a lambda function the linear mean squared error on X and Y with first coefficient, second coefficient, A and B. You need to give it an initial start guess, which we're going to start off at 0, 0. And then it's going to return the residual.x is going to be the best NumPy array. And what we're going to see when we do this procedure is that our best A and our best B turn out to be 0.97 and 1.01. So that looks pretty darn good. And there's going to be a bunch of like fancy machine learning algorithms we're going to learn about next week. And they're all implicitly using this function under the hood if you check their documentation. So let's see how well this thing works. We're going to test this thing on the number 0.7. And, well, our function is y is equal to x plus 1. So when I press enter, if we did a good job, this should come out with a number that's close to 1.7. Close to 1.7, 3, 2, 1, go. 1.698. Pretty darn good. All right, that's it for this video. Thank you for bearing with the bonus material. I'll see you guys again next time.